Okay, hello everyone. Hope you can hear me okay. Thank you very much for joining us today. My name is David Rodriguez, and today I have the pleasure of introducing the first of a series of 4 seminars on the topic of space propulsion given by Professor Koizumi. Professor Koizumi is an associate professor and head of the Space Propulsion Lab at the University of Tokyo. He's also the chief technology officer at Payload Inc., a company founded in 2020 and dedicated to develop water-based electric propulsion technologies. And since July this year, he's been with us here at EPFL as a guest. Previously, Professor Koizumi worked as an assistant professor in the Institute of Space and Astronautical Science at JAXA, the Japanese Aerospace Exploration Agency, and holds a Bachelor of Science in Mechanical Engineering from Keio University and a Master of Science and a Ph.D. degree in Aeronautics and Astronautics from the University of Tokyo. So before we start, just a few housekeeping rules. This seminar is being recorded, so make sure to turn off your cameras and please mute your mics. If you have any questions, I'm assuming we'll have a Q&A at the end of the seminar. So either write your question in the chat, or if you want to ask it directly, just raise your hand at the end and you will have a chance to ask your question. And without further ado, Professor Koizumi, the floor is yours.
Okay, thank you for introduction and a very long introduction. Thank you very much.
Sorry.
Yeah, and thank you everybody. Thank you for coming. So now how many people? 27. Yeah, thank you for a lot coming. And I'm glad to have this kind of chance here at EPFL. And Candice, thank you very much for organizing everything. So I'm very happy. Okay, so let's start. So this is, so first, let me talk about the seminar itself. So as David introduced, this seminar includes 4 talks. And today is our first talk and the principle of the rocket propulsion. And 2 weeks later, I have a talk about the chemical propulsion. And next year, I have 2 other talks about electric propulsion and micro-propulsion. And this is the seminar itself. And this is today's outline. So first, I want to start from the who am I? So I will introduce myself a little bit more. And after that, I will talk about these topics, what is delta V and how to get the delta V and how to throw what. So this seminar is basically a fundamentals of propulsion systems. And today, especially, it's a principle of the rocket propulsion. So main target of this talk is students in the university and maybe who are belong to the Department of Aerospace, but maybe some are not aerospace and mechanical engineering or something, but they are my main target. So by the way, how many audience now are how many students? So could you take some kind of reaction? If so, I'm pleased. So now 27 participants, but if you are students, please raise your hand by using the Zoom function. Not so many. Something like that. Yeah, thank you very much. And how many are propulsion specialists? Oh no. Okay. So this talk is not for propulsion specialists. So, but yeah, you are also welcome. Okay, thank you very much. Okay, so let's start. So I'm starting from who am I? So what you are seeing is Koizumi. I'm Hiroyuki Koizumi full name. So this is, you see, Japanese characters. So in Japan, we have 3 types of characters, and Chinese character, hiragana, katakana, and yeah, we have a lot of characters. So, and in the English, Koizumi Hiroyuki. Yeah. So Koizumi is a family name, and Hiroyuki is a first name. But simply, please call me Hiro. Okay. And my specialty is space propulsion and plasma engineering, and also small satellites. And also here I'm gonna show you some my favorites. So my favorites be sake. Sake is a Japanese rice wine. So you see right hand side, you see a lot of bottles. These are all sake bottles, and all are empty by me. So it's my favorite. And you see very fancy appearance on the bottom. Yes, I love these kind of a lot of stickers. And actually, I'm collecting the stickers. After I drank the bottle, I peel out and filing. And also ramen. You may know ramen. It's a Japanese noodle. It's originally from China. However, in Japan, we modified a lot. So it's a ramen. And my favorite food. In here, Switzerland, you may find some ramen shops, but in Japan, variety and the taste are so different. So if you someday, if you come to Japan, please visit Japanese ramen shop. And also I like to ride a bike, road bike, and also ice skating I love. But this is in the state of in Japan. So here now in Switzerland, my favorite is a little bit changed. So beer and sake. Yeah, actually in Japan, I can find a lot of beers, but here in Switzerland, the number is different. So many, maybe 10 or 100 times types of beer. So instead of sake, I started to drink beer here. So I'm actually enjoying this kind of beer. So right on the side, you see tiny amount of my collection of beers. So I love beer. And also instead of ramen, here I'm enjoying the cheese and ham. Yeah, in Japan, we can get some cheese and ham, but varieties are different. So here, huge number of cheese and ham. So I love those. And the road bike. So I actually brought my road bike from Japan to Switzerland, and now I'm enjoying the cycling here, especially along Lake Leman. I love this landscape, so very beautiful. Okay, so this is about myself, and do you understand me? And after this is my history in the space community. So as David introduced, I'm the associate professor at the University of Tokyo. That before that I was in JAXA, and before that I did my PhD in the University of Tokyo. So briefly, let me introduce these activities. So first, I started my space activity from the pulse plasma thruster. This is a kind of space propulsion, especially micro-propulsion, which is using a pulse discharge. And at that moment, I used a liquid propellant for this pulse discharge, especially water. And we injected liquid into vacuum, and after that, we break down the electrodes and generate pulse discharge. So this is a micro-propulsion. So at that moment, microsatellite and micro-propulsion had attracted attention in the world, and we studied this thruster. But this study is purely academic, so there was no application at all. And actually, as academic work, it was very fun, but as an application, we could not generate a good result. So, so far, no application. And after this PhD work and postdoc work, I moved to JAXA, Japanese Space Agency. So at that moment, asteroid sample return program, Hayabusa 1, was running in JAXA, and I was involved in that project. Actually, my expert is electric propulsion, and Hayabusa 1 employed ion thruster for that main engine. Then I was involved in this ion thruster operation team. And for years, we operated ion thruster. It was a very nice experience. And also, finally, this Hayabusa 1 brought back capsule to the Earth. And that capsule was dropped into Woomera Desert in Australia. So we team went to Australia to pick up this capsule. It was also a very nice experience. Actually, what you see here background is a picture I took in Woomera Desert. At that time, capsule landed on the desert. So you see, we asked also a background, very beautiful skies. You see Milky Way and also Southern Cross around here. Yeah, very nice experience. And from 2011, I moved to the University of Tokyo, and I started laboratory. So as a laboratory director, I started to manage my lab. And here, I decided to conduct research. Of course, it's a university, but also simultaneously, I started the project inside the laboratory. So the experience in JAXA was very valuable, and we knew the importance of the actual project, space project, not pure academic for academic. So academic for space application. So in my lab, we started several projects together with several research activities. So here I cannot introduce all of my activities. So I pick up a tiny part of my research and project activities. So here you see ion thruster. This is ion thruster, ion beam, and above is here is a neutralizer, so electron emitter. So this works as ion thruster, and we developed a very low power ion thruster, which is compatible with small satellite. And after that, we developed a propulsion module, and we installed this module to two microsatellites. One is Hodoyoshi 4. Hodoyoshi is a Japanese, it means so good. So good quality satellite. So not too extremely high quality. So this is a good point of microsatellite. This is a 60 kilogram class microsatellite. And also other one is a PROCYON. It's actually very rare. I mean, it's an interplanetary satellite. So in that sense, it's not a satellite, a space probe. So we installed this ion propulsion system to these two satellites, and we operated those in space. And also, as a latest topic for us is AQUULEUS. This is a water-based propulsion system. So we eject vapor to outside. And this AQUULEUS propulsion system was installed to the 6U CubeSat EQUULEUS. Its size is like this, so very small. And this EQUULEUS was now inside the SLS, gigantic NASA rocket at this part, together with other 10 CubeSats. And now we are waiting its launch. Hopefully next February, this rocket will be launched, and we will start the operation of this satellite and also this propulsion system. And then finally, another news for me is actually last year, 2020, some of my lab graduate, Ph.D. graduate, founded a new company called as Payload, the startup company, and where they are developing several small propulsion systems for CubeSat or microsatellites. So a system and ion thruster and hybrid. This hybrid means combination of ratio jet and ion thruster. By using the same propellant water, we install a ratio jet and ion thruster into very small package. By sharing the propellant into two types of thrusters, we can miniaturize the whole system. So now a couple of space projects are ongoing. Okay, so I finished my introduction. So let's go to the next part. So very basic point of the propulsion. What is delta V? So as I said, I came from Japan, so almost 10,000 kilometers away from here to here. So when you talk about the journey on the ground, on the Earth, distance is very important index for the journey. So 10,000 kilometers away is very far away, and it's very tough travel. But how about in space? So in space, of course, distance is a very important index. However, all of the subject stuff are flying, like this satellite, like a moon around the Earth. So even if the spacecraft is broken, it will fly millions of miles. Or even if you stand on the Earth is around the sun. So by 1 year, you are flying millions of miles. So in that sense, in space travel, distance itself, especially flight distance, has little meaning. So what is important in space is the delta V. So how you change the velocity of the spacecraft or yourself. So for example, satellite orbiting around the Earth. And at a certain point, when you change the velocity like this, you can change the orbit like this, from circular to orbit, or orbit to hyperbola. So changing the velocity is a very important activity in space, and it becomes a very important index of space journey. So when we talk about the propulsion and its ability, we always use this index, delta V, velocity increment. So for example, this is a typical delta V values from the Earth. So after you escape from the Earth's gravity, to go to the Jupiter, you need maybe 10 kilometers per second delta V, or in the case of Mars, 6 kilometers per second. This is in the case of the spiral orbits. But what I want to say here is that the order of delta V is from 1 to 10 kilometers per second. The order. And as to this delta V, here I want to say 3 points, important points. First is that it differs by the orbit, and the deceleration is the same as acceleration. And the third point is that it's not actual velocity change. So let me explain those. So first one is different by the orbit. So here I pick up two very typical orbits, orbit transfer, Hohmann transfer orbit, and Hohmann orbit transfer, and spiral orbit raising. So first one, Hohmann. It's very famous orbit transfer, and it's called as a two-impulse orbit transfer. So your initial orbit departure is this red circle with a radius of R1, and the destination is final orbit is this blue larger orbit with radius R2. And by using two impulse, two kick, here and here, you can change the orbit from this red circle to blue circle by using these two delta V's. And second example is a spiral orbit raising. It's a continuous thrust orbit transfer from the same departure, initial orbit R1 to the destination R2. In this case, the solution to obtain the solution is a little bit difficult, and I need some assumptions. But in the case of very low continuous thrust, and if these assumptions are satisfied, we can obtain very simple result for the required delta V. It's just a difference of the orbit velocity of this red circle and blue circle. So here our purpose is a comparison of these two orbits transfer. So both orbit transfer has the same departure and destination. And this graph shows a comparison. So vertical axis is a delta V normalized by the initial orbit velocity V1. And the horizontal axis is a ratio of a radius of two circular orbits. So R2 by R1. So for example, 10, this means a 10 times larger orbit radius. So you see from 1 to 2 or 3 around here, spiral orbit raising and Hohmann transfer required delta V is almost same, almost these two curves are overlapping, and it means not so much difference. But in the case of 10 or 100 or more, the required delta V for spiral orbit raising and Hohmann transfer were very different. So you see almost 1.5 times difference, or almost 2 times difference. So even if destination are same, required delta V is different by how you change the orbit. Okay, second point is deceleration. So for example, from the Earth, if you want to go to the Mars, about 3 kilometers per second impulse kick is enough to reach to the Mars. So from Earth to the Mars. So this is one of the very simple way to go to the Mars. And other case, if you want to go to the Venus, so in our planet, you need to decelerate your spacecraft. Then you will decrease the radius of your orbit, and you may reach to the Venus. In this case, you need about 2.5 kilometers per second deceleration. But this is deceleration, but actually acceleration in opposite way. And what I want to say is, on the ground, in my image, in your image, acceleration is harder than deceleration. So deceleration is simply done by brake, and sometimes it's easier than acceleration. However, in space, deceleration is hard as acceleration, so no difference basically. Only the difference is the direction. So even the deceleration, we need the same effort for acceleration. This is the basic principle for delta V. Okay, so final point, third point. It is not actual velocity change. You may think that I'm saying a very funny or curious statement, but what I want to say is like here. So I'll show you one example. So let's consider orbit change from low Earth orbit. It's altitude 420 kilometer, and at that moment, orbit velocity is 7.66 kilometers per second. And by continuous thrust, you can raise up your orbit from red to blue, as I said, by spiral orbit change. And actually, by continuous thrust in the direction of acceleration, you can increase the height from 400 to 600, like this. But as a result, your spacecraft velocity is decreased. Actually, it becomes 7.55 kilometers per second. You are accelerating the spacecraft. However, your spacecraft, its velocity is decreased. This sounds somehow curious, but what occurs here is very simple. Actually, the energy of spacecraft is increased, but just kinetic energy is decreased. So sometimes this kind of things happen in acceleration or deceleration of spacecraft. So if you substitute these values to the total energy of satellite, you will find that actually total energy of the satellite is increased from this maneuver. So delta V, its actual meaning is a virtual velocity increment. It's not actual velocity. So this virtual velocity means that the spacecraft would gain if no other force applied to it. So it's a kind of virtual velocity. So please distinguish from the actual velocity increase. And its calculation is very simple. By dividing the force by mass and just integrate it, you can easily get the delta V. So this is a this is a velocity increment. In the world, there was nothing other than satellite. Okay, so this is that. And the next topic is how we get that delta V. So far we have understood that we need delta V, and next point is how to get it. So for that we need acceleration. It's obvious. And on the ground, it's somehow easy. And on the ground, or in the ocean, or in the sky, always we are pushing something to get the acceleration. In the case of on the ground, when you are running, your foot is pushing the ground. And in the case of the boat or ships, your propeller or oar is pushing water. And in the case of airplane, it's pushing air from front to the back side. So this is a basic principle of acceleration. So always we need to push something. However, what is troublesome is in space, nothing to push. It's very troublesome. Then we need to bring something to push. And this method for acceleration is called as a rocket propulsion. So this is a definition of rocket propulsion. So in that sense, the material or the stuff you threw out is anything is okay. So this pen or this markup, anything is okay. If you threw out it to outside, you will get somehow reaction. and you will be accelerated somehow. And also here I want to emphasize some terminology. So the stuff we threw out, we call it as propellant, the stuff material to propel to accelerate something, propellant. And there are similar two words, fuel and oxidizer. So especially on the ground, sometimes fuel is used instead of propellant. But in space propulsion, basically these terms are definitely different. So fuel means substances that are oxidized in combustion. And oxidizer is a substance that oxidizes that fuel in combustion. So fuel and oxidizer both become propellant. But the propellant and the fuel, these two terms are not equal. So when you use these two words, please distinguish those. Fuel and oxidizer can become propellant. And especially some propulsion system does not use fuel or oxidizer at all. Some, especially electric propulsion, in that case, they use just propellant only. Okay, next, let's derive some basic relation for this mass ejection and acceleration. It's called as a rocket equation. And some of you may have known this derivation, but here I wanna again show you. So let's assume the spacecraft with a mass of msc. This sc means a spacecraft, and this tiny amount of propellant delta m is released at the next moment. And first, the spacecraft has a velocity small v to left-hand side. And after the separation by reaction, this spacecraft will gain some acceleration. As a result, velocity would be increased somehow, delta v. So this delta v is different from that we talked before. So this is just a small, tiny amount of velocity increase by this mass ejection. And this delta m is ejected from the spacecraft with a relative velocity ue. And this mass will have this kind of velocity from the inertial frame. And this equation is a simple momentum conservation. And by after some algebraic manipulation, we get this kind of. I forget to use this. Yeah. So you get this kind of relation after neglecting the second order terms. And let's divide by delta t term. So you get this kind of differential equation. And you see here, this becomes force. So this is called as thrust. So thrust is a dm dt times relative velocity of the propellant. And sometimes we write this dm dt mass flow rate as m dot derivative of mass. Okay, so this is a thrust. And also on this slide, I'm doing another manipulation. So this is a basic same equation from the momentum conservation. But here I used this relation. So here I want to focus on the velocity change of a spacecraft in long time. So before I talked about the short time change of the spacecraft velocity and force. But here I want to deduce the long time velocity change. And the ejected mass is related to the spacecraft mass by this relation. So from the spacecraft, it's a reduction of the mass. So small delta m is equal to minus delta m of the spacecraft. So this relation, and changing to this and integrate from T1 to T2. So at the moment of T1, spacecraft has an initial mass. So here I means the initial. And as a time 2, spacecraft has a final mass and final. So by simply integrating this equation, we got this kind of equation, and it can be easily solved like this. And this is called as rocket equation. This is a very famous equation in this field. So delta V is proportional to the relative velocity. It's called as the exhaust velocity of the propellant, and log and mass ratio. Mass ratio means the ratio of initial mass by final mass. So MR is mass ratio. And this is its inverse form. So if you wanna know the mass of propellant, you can use this equation instead of the log equation. So this is so famous equation. So I think most of you know this equation. But this is a graph of this equation. So you see the velocity increment as a horizontal axis, and the mass ratio is a vertical axis. So, and also you see several colors, and these colors, each color means a different exhaust velocity. And this table shows several exhaust velocity of launch vehicle. So some are very famous. So Ariane 5, you know a lot, or Space Shuttle, or Japanese A2A rocket. So these are exhaust velocity of these levels. So here, I don't want to emphasize the details of these numbers, but I want you to watch the numbers, the range from minimum one would be 2.7 and the maximum would be 4.6. So the range of launcher exhaust velocity is around 3 to 4, roughly. So in this graph, it's this yellow line. So in this line, so if you want to get a velocity increment of 10 kilometers per second, the mass ratio becomes, this is 20, maybe 12 or something like that. And the mass ratio 12 means final mass is about 8% of the initial mass, so something like that. So less than 10% will remain after the acceleration. So this is what I said. So in the case of if you use 4 kilometers per second exhaust velocity, and if you want to get 10 kilometers per second, the available percentage is just 8%. But do you use this 8% for the payload? This is a very big problem, because any rocket cannot fly only by the payload and the propellant. We need some structure, like an engine itself. It weighs somehow, and the tank, and the body structure itself. So we need to take account those other mass. And to introduce those effects, we have this kind of coefficient, structure coefficient. Its definition is a mass of structure. This means like engine, tank, body itself. These are all included into this mass, divided by propellant plus structure mass. And of course, we wanna decrease the structural coefficient as much as possible, decrease as less as possible. But practical launch vehicle or spacecraft has this kind of value, 0.2 to 0.2. And we need to incorporate this structural coefficient into rocket equation. So basically, rocket equation itself is the same, but the content of initial mass and final mass is a little bit different. So here I included payload mass and structure mass, and the difference is only propulsion mass, propellant mass. And after some algebraic manipulation, you can obtain this equation here. Lambda is a payload ratio against initial mass, and this epsilon is a structural coefficient. And this equation tell you very important point that there is a maximum velocity by rocket equation. There is a limitation. So actually, to increase this delta V, you need to increase inside of logarithm log. And for that, you need to decrease this denominator. And to decrease this, you need to decrease this payload ratio. But you know that its minimum value is at 0. Meaningless rocket, but it's a theoretical minimum value. And at that moment, you can easily the delta V by this equation. And it is a maximum delta V obtained by this rocket propulsion system. And depending on the structural coefficient, delta V max is simply the exhaust velocity times constant. So in the case of the 0.515 structural coefficient, delta V max is a 1.9 times U. So I missed the subscript E. And the exhaust velocity, if you assume the 4 kilometers per second, the maximum delta V becomes 4 times 1.9. So it's less than 8. So we need some kind of limitation. And to overcome this limitation, the measure that we use is a staging. So this concept, I think you know well. And also, rather than this my poor drawing, please imagine this kind of rocket. And actually, this picture is a Japanese toy, not the actual one, Japanese toy. But this is a toy for not for. This is a toy for not children, for adults like me. So actually, the price of this is 50 francs or something like that. Not 50. 500 francs. Yeah, sorry, 500 francs, something like that. So not so cheap. I cannot give this for my children. So. And the reason this is so expensive is this is very, how to say, detailed. So you can separate each stage. So you see first stage, second stage, and the third stage, and also lunar orbiter. Very good toy. But at that moment, I have not bought. I didn't buy this toy, but I should have bought. But anyway, by using this kind of staging, we can increase the delta V somehow. So next, let's see this effect. So there are some equations and symbols. But here, let's consider the nth stage rocket, multi-stage rocket. So first stage, second stage, and multi-stage. And structural coefficient, its definition is almost same as before. So for each stage, we can define structural coefficient. So MPI is a ith stage propellant. So in the case of the first stage, MP1 is a first stage propellant, and MS1 is a first stage structure mass. And let's define structural coefficient like this. And also payload ratio. So for first stage, anything above that, I mean this part, is a payload of first stage. Okay. And for second stage, this part is a payload of the second stage. So let's define payload ratio of each stage. And the mass ratio is also defined like this. And introducing this definition by simply using the rocket equation for each stage, we can get each stage delta V. And simply simple summation of these delta VI, you will get this total delta V by this equation. So somewhat this equation is complicated, but what we are doing is very simple. So just calculate each stage delta V and just summation of these. And also total payload ratio. This should be defined by the M1. M1 is a total rocket mass and the ratio of the payload. So this is the same definition. And if you see the definition of payload of each stage, you will understand this total payload can be described by this simple multiplication of each stage payload ratio. So by using this equation, you can calculate multi-stage rocket delta V. So this slide shows us some kind of example. So, for example, in the case of total delta V of 0.037 and the structure efficiency 0.15 and exhaust velocity 4 kilometers per second. By 3 staging, we will get the total delta V of 10 kilometers per second. And let's compare this value with a single stage rocket with the same exhaust velocity and the same structural efficiency and the same payload ratio. And you will get from this single equation, you will get this delta V, 6.8 kilometers per second. So you see difference from 10 to 6.8. So this is the effect of the staging. And this graph shows the result of this staging. So vertical axis is a total payload ratio, and horizontal is a velocity ratio, delta V divided by exhaust velocity. And this color shows the difference of the staging. So this one is a single stage simple rocket, and the second stage and the 2 stage and the 3 stage rocket. These are very common for the current launch vehicles. And also you can calculate the infinite stage rocket. It's impossible, but we can calculate, we can consider such kind of limitation. And you see, even if you introduce this staging concept, there is some kind of maximum, so around here. Not, you cannot increase the delta V to the infinite. And this is other case. Of course, if you can reduce the structure quotient, total payload ratio is a little bit increased. Okay. And the final part of this chapter, I want to talk about the actual method to calculate the delta V of the launch vehicle. So what I want to say here is a typical rocket has launch rocket booster like this. So this is a Japanese A2A launch vehicle, and it has a main engine, liquid engine here, but simultaneously it has booster. So it's the same as a Ariane 5 rocket. So in this case, we have 2 kinds of exhaust velocities. The main engine have a 4.3 kilometers per second exhaust velocity, but the solid rocket booster has a 2.78 kilometers per second. So in this case, how do you use the rocket equation? So for that, let's introduce effective exhaust velocity. Definition is very simple. So F total is a total thrust. So in this case, the thrust of all of these first stage thrust, rocket booster plus liquid main engine. And let's divide it by m dot total, mass flow rate of all of the engines. So by using this definition, we can use the same rocket equation. So for example, in the case of the A2A first stage, we have these kind of values for main engine and solid rocket booster. So thrust and mass flow rate. So simply calculate, use the total thrust and total mass flow rate. You can get this effective exhaust velocity. This is just a mean velocity weighted by mass flow rate. So in this case, in this kind of case, please use this kind of effective exhaust velocity. So I used the subscript E for the exhaust velocity. This E means that, yeah, So how to throw? Okay, so we have known that we need delta V, and to get delta V, we need rocket propulsion. And rocket propulsion means that we need to throw out something to outside. And for this action, throwing, what do we need? And of course, we need mass, something to be thrown out. And also another point is energy. So in this sense, rocket propulsion is a device to convert some energy to kinetic energy as a final state. So propulsion system is a device like this. Input is energy and mass, and output is impulse. So left-hand side is energy conversion equation, and right-hand side is the same. And the left-hand side is this is power. So energy per unit of time, and mass flow rate. This is a mass per unit of time, and F is a impulse per unit of time. So this is a per unit of time version. And the right-hand side is a gross energy and mass and impulse. But anyway, this relation is very important for rocket propulsion, and we need energy to get kinetic energy. Okay, so in the world, there are a lot of types of energies. So you see some fancy energy source like antimatter or nuclear fusion, but yeah, there are a lot of types. And when we think about we need to convert energy to kinetic energy, you will immediately understand this mass energy density would be very important. So lightweight and high energy, it means very high exhaust velocities. So energy density would be very important. So for these many energies, this slide shows the energy density. So a wide range. So yeah, antimatter annihilation is very excellent. So yeah, for this calculation, I used this equation. So all of the mass should be converted to the energy. So very high, extremely high energy. And in the case of nuclear fusion and the nuclear fission, so in this case, fusion, I used this equation, and fission is a plutonium. But anyway, they are very high energy. And the chemical energy and the electrical battery, not so high. And also another energy source is a solar power generation. But this is a little bit different from others because you see the unit is different from the joule per kilogram, and here joule per second squared meters. About this, let's discuss later. Okay, so for these energy sources, let's see the details one by one. Okay, so the first one is antimatter and nuclear fusion. So antimatter, you may think it's kind of a scientific fiction, but not. Actually, just from here, 60 kilometers away in Large Hadron Collider, they are producing antimatter. So human beings has a technology to produce antimatter. And actually, somehow we have a technology to contain those. But currently, the maximum time for container is 100 seconds or 1,000 seconds, not so long. So antimatter, in the point of energy density, it's ideal material. However, we need to find the method to generate those more effectively. Maybe 10 to the 10 times more effective method we need. Or also, in the point of container, we need 10 to the 6 times longer keeping is necessary. So it's possible, but not now, I think. And in the case of nuclear fusion, first, let's wait the ITER. So after it works well, let's bring it to the space. Maybe, hopefully 20 years later, or 40, I don't know, but yeah. Well, actually, yeah, it's ongoing project, so I'm waiting. Yeah, but here let's do a little bit calculation for fun. I mean, if you can utilize this energy for propulsion system, what happens? And this calculation, I think it's very interesting and interesting result we can get. So here, let's define MR is a rocket mass. It includes a payload and antimatter container or nuclear reactor, but any kind of rocket mass. And ME, energy source mass. This is antimatter itself or nuclear fuels. And MP, this is the mass of the propellant. Of course, we can use this energy source as a propellant, but also we can add some material as a propellant. So let's assume this amount. And here, alpha is the energy density coefficient. So energy obtained by this ME is like this. And when we think about this kind of propulsion system, I don't know what kind of system can contain antimatter for 10 years, but I'm sure that this antimatter mass would be much, much less than the rocket itself. I'm sure that. So let's use this assumption. So energy source mass would be much less than the rocket itself. It means less than antimatter container or nuclear reactor. And maybe propellant mass would be compatible with the rocket itself. So by using this assumption, you can calculate the exhaust velocity by this simplification. So energy source is this ME, and this energy is sent to the propellant mass, and it gets this exhaust velocity. And the initial mass can be written as mass of rocket plus mass of propellant. So we can neglect the mass of energy source. Then by applying rocket equation, you can get this kind of simplification. So you see here, exhaust velocity is determined by energy and the rocket of mass, and times function f. And the function f is a very simple function of log and square root. And for this x, we are using the ratio of propellant mass and the propellant rocket propellant mass of rocket. And when you see this function f, this has a maximum. So if you draw this function, it becomes like this. So there is a maximum point. And this maximum point obtained at x is equal to 3.921, blah, blah, blah. And at that moment, this function reached to the maximum point of about 0.8. So whatever you use for the energy source, under this assumption, the best propellant ratio is decided like this, about 4. So ratio of propellant mass to rocket mass. And by using this ratio, we can obtain delta V max. So by this equation, you can calculate delta V max of antimatter rocket propulsion system. And it's very important or interesting point is, as I said, nuclear fusion, antimatter. So those types itself is not so big problem. The point is a ratio of this energy and rocket mass. And this rocket mass includes a nuclear fusion reactor or antimatter container. So this means this mass and obtained total energy. This ratio is very important. This ratio determines the delta V. And for example, in the case of the antimatter of 1 gram, tiny amount, but huge energy, and the container, let's assume 10 ton. And eta is the efficiency, and let's assume 50%. And in this case, you will get delta V of 76 kilometers per second. You may think this is very high, but yeah, actually, compared with actual ongoing satellite mission, this is quite high value. But for me, by using antimatter, I want to much more delta V, like 1,000 or 10,000 kilometers per second. So we need a lighter weight container, like a 1 ton or 100 kilogram. Then you will get a fantastic delta V. Okay, anyway, let's go to the next topic. It's a nuclear fission. And for nuclear fission, there are two types. First one is a nuclear reactor, nuclear fission reactor. Actually, nuclear fission reactor, it's practical technology. So you know that the nuclear power plant uses this reactor. And actually, its miniaturization is also practical, actual technology, existing technology. So this is just a design case by Toshiba, named as 4S, small nuclear reactor. And also, you know that the nuclear submarine or other things there exist, so it's possible. And also, its space application. There are some kind of technology design or test already, especially in former Russia, Soviet. They designed and built and tested space application of a nuclear fission reactor. So I say, in the technology point, technically it's possible. And the problem is politics. Yeah, it's a very big point. So if you want to develop this kind of space application, you need a very good politician, I think. But many areas, so this is my impression for nuclear fission reactor. And another technology for the usage of nuclear fission is RTG, radioisotope thermoelectric generator, or nuclear fission battery. And actually, it has already been used for many missions, especially from NASA. And this picture is a Cassini, and it installed 3 nuclear batteries here and here and here. And it's practical technology. And typically, it uses plutonium, this special isotope plutonium, and it has very high energy density. If you compare with chemical reaction, you know that it's highness. But there are 2 points. First one, in the case of this radioisotope usage, it gradually releases the energy. So in this case, plutonium, it releases all of the energy by using 3 or 4 or 500 years, very long time. So, and actually, initial state, its energy emitting ratio is about 500 watt per kilogram. And also, second point is this 500. This is also higher than the chemical reaction. However, this 500 is a thermal energy, and we need to convert to electrical energy to use as a battery. And that conversion is very low efficiency. So conversion from thermal energy to electrical energy is not so good idea. So thermal energy is a very low state of the energy. So as a result of this conversion, actual device like this, its power ratio is like this, 5 watt per kilogram. So it's not so high. So actually it's lower than the solar array panel. Okay, so next is a chemical reaction. So compared with the previous example, energy density is lower than the antimatter and the nuclear, but storage ability and handling ability is very nice. Also, we need some kind of cryogenic system or some kind of toxic material, but it's manageable. So we can use chemical reaction or actual propulsion system. And let's calculate that effect. So in the case of a chemical reaction, one feature is this energy source, mass of energy source. This is used as a propellant. And so in this equation, both sides, you have energy, mass of energy source. Of course, you can add additional propellant to that, but yeah, usually common chemical propulsion uses this energy source as a propellant. So ME is a propellant. And you see that from this equation, exhaust velocity becomes this value. And this exhaust velocity is determined by this alpha, so ratio of the energy density. So if you select one chemical reaction, this exhaust velocity is fixed. And after that, by log, delta V is determined. And as I said previously, inside this log, we need to have structural efficiency. And due to that, this log has also limitation. In the case of the certain structural coefficient, this limitation becomes like this. I think this is a case of one. So this means if you select material and if you have a limitation of the structural coefficient, delta V is limited. So in this case, as I said, delta V is limited like this. Okay, so next is electrical battery. So honestly, in the point of propulsion system, electrical battery is not so attractive. So it's a very important component for spacecraft. It's used as a buffer of the solar power generation in spacecraft, but in the point of energy density, its density is much lower than the chemical reaction. And usually we don't use it for propulsion directly. So rather than this, we should consider this solar power generation. So solar power generation is different from other example, as I said before. So its energy depends on how long you generate the power. So around the Earth, solar power is this value per unit time and per unit area. So 1.4 kilojoule. So depending on the time, the energy you got is changing. So in the case of 1 day charge, the energy density will become like this by assuming the typical value for the solar cell. And this is less than chemical reaction energy density. And in the case of 1 month, 2.6 megasecond, the energy density becomes like this, 130. So it's higher than chemical. And by 1 year solar power generation, you will get more than 1,000 megajoule per kilogram. So it's much higher than chemical energy density. So in the point of the solar power generation for the usage of propulsion system is this time. So we need time to generate higher power, higher energy. So this is a summary of my energy talk. For antimatter and nuclear fusion, we have to wait. And the nuclear fission, it would be our next step. And the electrical battery should be combined with solar power. So currently, our candidate is a chemical and electric, especially solar power generation. And by chemical reaction, its usage is a chemical propulsion, and the solar power generation, its usage as is solar electric propulsion. And finally, briefly, let me talk about the characteristic of this chemical propulsion and electric propulsion. In the case of chemical propulsion, you can freely use the stored energy in the point of time. But you must increase the mass to increase the total energy. So in the case of the time to generate impulse, there is a flexibility. So you can arbitrarily choose how much mass is used as a propulsion system. So it's very, you have a flexibility. However, there's a limitation for the this. So mass of the energy source and impulse. But in the case of electric propulsion, you can freely choose the energy to mass ratio by just increasing the charging time. But as I said, you need to increase the charging time for energy. So in the point of time, there is a limitation. You need to charge. You need to wait. But after the waiting, you can flexibly select this ratio, impulse by mass. So this is a difference of Cp and Ep. And it becomes a difference of thrust and exhaust velocity. So impulse by time, this becomes thrust. So chemical propulsion is very flexible for the thrust. But it's not flexible for impulse by mass. It's determined by the chemical reaction combination. So you have a limitation for this exhaust velocity. Instead, in the case of electric propulsion, there is a limitation for thrust. This is an impulse by time. So impulse by unit time, there is a limitation. And impulse by time is a thrust, as I said. And there is a limitation for thrust. But by changing the charging time for solar power, you can increase the ratio of impulse to mass. So this means you can really select the exhaust velocity. So chemical propulsion is good for short time, and short time is a high thrust missions, but you need a massive rocket or propulsion system. And for electric propulsion, you can reduce the mass and you can develop compact rocket. But instead, you need very long time to get meaningful energy. So this is a essential difference of chemical and electric propulsion. Okay, sorry for a little bit longer talk, but yeah, this brings the end of my first talk. So thank you for your attention.
Thank you.
Thank you. So we open the floor now for questions. Just whoever wants to go first. I see a lot of hands up. How we do this?
No, it's clapping.
Oh, they're clapping. Okay, that's better.
Yeah,
But
if you have questions, you can raise your hand or type in the chat if you're shy. Otherwise, I'll unmute you if you want to speak up.
I was surprised to see the energy for the radiation 500 watts per kilo.
By isotope, I see plutonium. Yes, this one. Yeah, quite high.
Yeah. Is it high?
High, yes.
But 500 watts per kilo. If you have 1 kilo and you can extract only 500 watts.
But the watt almost forever, 100 years.
Oh, yeah.
So the total energy is very, very high.
Yeah.
So actually, half lifetime of this plutonium is almost 100 years. So after 100 years, this value will become 270 or something like that. Yeah. But still you can use. Okay. So in that sense, very long time battery.
Any other questions from the audience? Oh yeah, we have a question from Sungwook. Hey Sungwook. So he said, does delta V map in the beginning assume EP spiral?
Yes, this is a spiral orbit case. So this is a case of EP. So usually when you go to the Mars, you use a Hohmann transfer orbit and actually only fast kick. So you don't need 6 kilometers per second. But by comparison, I just used a spiral orbit case. And the reason is that calculation is very easy, just a difference of the circular orbit.
Okay, thank you.
So this 6 kilometers per second is
It says many thanks.
corresponding to around this blue line.
Okay. So,
Yeah, I don't see any more
No,
hands up nor
no.
clapping. So maybe we can wrap it up here. Thank you again,
Yeah.
Professor Koizumi.
You're welcome.
And when is the next one? You showed the slide, the next seminar.
2 weeks later. So
December 16th.
December 16th. Okay. So yeah, I hope you can all join us for the second seminar. Thank you again, and have a good evening.
Yeah.
See ya.
Thank you, everyone.
Bye.
Thank you.
Bye-bye.
Bye-bye.